Okay, in this video we're looking at 2021 paper 1 question 9, and we're basically starting off with a log problem here. In this problem, the capital T represents the temperature of a cup of coffee, and the small t represents the time since the coffee was brewed. The formula we're given is that T of t is equal to AE to the power of minus 0.81 t plus 20, where A we're told is a constant. Now, we're asked to show that A is equal to 75. And to do that, you look at the very first sentence. The very first sentence that when coffee is freshly brewed, it's 95 degrees Celsius. That's the only real information we've been given. When it's freshly brewed, the time since it was brewed is 0. So small t is equal to 0. And capital T, the temperature, is 95. We can use this information to work out what A is. So in this case, it just means you sub in. T of t, the temperature of the coffee, is 95 degrees. And that's equal to AE, and small t, the time since the coffee was brewed, in this scenario is 0. So this actually just becomes minus 0.081 times 0, and obviously the 20 is a constant, so nothing happens to it. But look what happens to the power of E there. It just becomes E to the power of 0, because 0 multiplied by anything is just 0. You should remember from your rules of powers that anything to the power of 0 is simply 1. So that means that the first term here is just A times 1. So I end up with 90 is equal to A plus 20, subtract 20 from both sides, and I end up with A is equal to 75. That's the solution for part I. In part II, we're asked to explain from this formula, what does the 20 represent? Well, you can think about it here. We know that when it's brewed, it starts off at 95 degrees. And obviously then, the longer we wait, the colder it gets. And this formula models the rate at which the coffee cools. So after 10 minutes, if I subbed in t equals 10, I'd work out, oh, maybe after 10 minutes, it's only 60 degrees, or it's certainly going to be colder. But the thing that's never going to change is the 20. So after 2 days, the 20 is still there. If I subbed in a really large number for t, this essentially becomes a 0. And essentially the coffee has cooled as much as it could possibly cool. But it's never going to go below 20 degrees. The 20 here represents the minimum, the coldest the coffee will ever get. So that's what I've chosen to describe here. 20 represents the lowest possible temperature of the coffee. Or in other words, that's the room temperature. And obviously the coffee's not going to get any colder than the room. After a long period of time, after a year, if you left a cup of coffee there, it would be 20 degrees, because that's obviously the temperature of the surroundings. There's a couple of different things you can go with there. You could explain it's the room temperature, or it's the coffee never gets colder than 20 degrees. In part 3, we're asked to determine the decrease in the temperature of the coffee after 10 minutes. In order to figure that out, first thing we have to do is work out what is the temperature of the coffee after 10 minutes. Well, we have our formula here, and notice now that I'm not using A, I'm using 75, because A is a constant. So once we worked out in part I that A was 75, it's 75 for the rest of the question. And we want to work out what is the temperature after 10 minutes. So small t will be 10. It's straightforward enough. You literally just sub into your formula. If you plug all of this into your formula with a 10 instead of a t, you end up with the temperature after 10 minutes is 53 degrees. I've rounded that one to the nearest degree. That's not what you were asked for though. You were asked for the decrease in the temperature after 10 minutes. From the first part of the question, we acknowledged that the moment the coffee is brewed, it's 95 degrees Celsius. 10 minutes later, it's 53 degrees Celsius. So to work out the decrease, we just subtract them. 53 from 95 tells me that in the first 10 minutes, the coffee decreases in temperature by 42 degrees. In part B, we're asked to work out how long is it going to take before the coffee is 82 degrees. So it starts off 95 degrees, how long before it's 82 degrees? So in that case, that simply means you're subbing in the capital T is 82. So you let 82 equal to the right-hand side of the equation. At this point, you should recognize that this is a logs question. The unknown is in the power. I need to find what small t is, and it's in the power, so it will be logs eventually. But before that, the first thing I decided to do was subtract 20 from both sides, in which case I get 62 is equal to this term. Now I want to introduce logs, but before I do that, I have to isolate the e to the power of the unknown. So I divided both sides by 75. Got 62 over 75 equals e to the power of this. Now I've isolated that e, so now the unknown is in the power, so I introduce logs. I decided to introduce the natural log ln, putting ln in front of the right hand side and ln in front of the left hand side. The reason we introduce logs is to use the rules of logs. And the third rule of logs on page 21 says if you've log of something to a power, you bring the power in front. So I just simply bring in front minus 0.081t ln e. And from here it's going to be relatively straightforward. Let's start it from the top up here maybe. The left hand side at the moment, I'll leave it as it is. It's just ln 62 over 75. But the right hand side, you should notice that ln e, that is actually just log e to the base e. Remember, ln is short for log to the base e. So that means, and that simply has a value of 1. So ln e is only 1, which means the right hand side is just minus 0.081t times 1, which I don't need to put in. My goal is to get t on its own. So to get t on its own, I'll simply divide both sides by the coefficient. So it'll be ln 62 over 75 divided by minus 0.081. I'll plug this into my calculator and get my final answer for t. So if we plug this into our calculator, we get 2.35. Now the question asked us to leave our answer to the nearest second, but it told us at the start of the question that t is in minutes. So this is 2.35 minutes. So we need to convert this into seconds. Now for this obviously 2 minutes, the number of seconds in 2 minutes is simply 120, so that's no bother. It's the 0.35 of a minute where you might run into bother. If you want to work out how many seconds that is, well obviously there's 60 seconds in a minute. So 0.35 of a minute multiplied by 60, that'll tell me the number of seconds that it's equivalent to. If you plug that into your calculator, it's 21. So the 2 minutes is obviously 120 seconds. The 0.35 is 21 seconds. So if I wanted to leave my answer in seconds here, it'd be 120 plus 21, which is 141 seconds. And that's my final answer for part B here. In part C, we're asked to find the temperature that the coffee has reached when T-T is minus 4.05. You should recognize this immediately. Obviously they're referring to the derivative. When the derivative is equal to minus 4.05, I want to find the corresponding temperature. Obviously the first thing we need to do is actually get the derivative. So T of t is given as this, and the first thing I'm going to do is try and find the derivative of that. So if I'm looking for capital T dash t, well the derivative of 20, it's a constant, so it's just 0. So we can ignore the 20, and we're actually just getting the derivative of this. We'll start off with the 75, the coefficient will remain in the answer, but it doesn't really affect the question. According to the log tables, the derivative of e to the power of something just stays the exact same. So I just rewrite it literally exactly as it was, but then I multiply by the derivative of the power. The derivative of minus 0.081t, well in that case it's going to be minus 0.081. That's the derivative of just the power. And this gives me t dash t, the derivative of the original equation. What I can use this for now is I can let this equal to minus 4.05. And I'll be able to work out the time when the first derivative is equal to minus 4.05. Then when I have the time, I'll be able to sub into this equation and get the corresponding temperature. So we've worked out that our derivative is 75 e to the power of this by minus 0.081. And now we can let that equal to what was given in the question, minus 4.05. At this stage you should notice that we've got one equation and one unknown, so we can solve and work out small t, the time at which the first derivative is equal to minus 4.05. So the first thing I decided to do was on the right hand side. Notice there's a 75 and then there's this, and they're both constants, so we can just multiply them by each other. 75 by this gives me minus 6.075. At this stage I notice that my unknown is in the power, so I'm going to have to introduce logs at some point. But before I introduce logs, I have to isolate the part of the expression with the unknown in the power. So I divided both sides by minus 6.075. Then when you plug the left-hand side into your calculator, you just get 2/3. And now I'm ready to introduce logs. I introduced the natural log ln onto both sides. Then I can use the rules of logs, so I brought e to the power, I can bring the power in front, and I get minus 0.081t ln e. Remember that ln e is simply just 1, so on the next line I just ignored it. And at this stage I decided to just get t on its own by dividing both sides by the coefficient of t. When I plug all this into my calculator, I get 5. That tells me that after 5 minutes, the first derivative is minus 4.05. But I wasn't asked for the time, I was asked for the temperature. So we're going to go back to the original equation, sub in small t equals 5, and get the corresponding capital T, the temperature. So I've simply taken down the original formula and I've subbed in a 5 instead of a t. When I plug the entire right hand side into my calculator, I work out that the temperature after 5 minutes is simply 70 degrees Celsius. In the final part of this question, we're told that a sugar cube is placed into the coffee cup. And obviously, if you think about it logically, if you put a sugar cube into a cup of hot coffee, the cube starts to dissolve, or the cube gets smaller and smaller. We're told that as this cube dissolves, it retains its cubic shape. So even if it's only half as big, it's still a cube. And that's important for what we're about to do here. We're told the rate at which the volume decreases is 1/20 centimeters cubed per second. First of all, hone in on the fact that the volume is decreasing. That means it should be negative. It's minus 1/20 centimeters cubed per second. This is a derivative, and they're talking about rates here, so it should be clear that obviously we're talking about derivatives here. It almost says it in the question anyway, that it's the rate at which the volume is decreasing. That'll obviously tell you that volume is relevant. One thing I always tell students to focus on is the units. Clearly centimeters cubed refers to volume and seconds refers to time. So if you didn't understand the question and you were just looking at the units, you'd be able to tell it's volume over time, or in other words, dV dt. dV dt, the rate at which the volume is changing, is minus 1/20 centimeters cubed per second. And then they told me to label one of the dimensions as x. So the length is x, the width is x, the height is x. Remember, in a cube, all 3 dimensions are the same. And they've asked me to find the rate of change of x at a specific time when the volume is 1/64. To get the rate of change of x, that means dx dt. So notice they didn't say get the rate of change of x relative to time, but if they just say get the rate of change of x, it's assumed that they're talking about time, because everything is relative to time. So the rate of change of x, we're looking for dx over dt. Now think back to the second last tutorial we did on differentiation. We did this a load of different times. If I'm looking for dx over dt, I'm going to use 2 derivatives from the question to work it out. On the top of the fraction, I want to have a dx on the top of one of these fractions. There's a dt on the bottom, so I want to have a dt on the bottom of the other one. And then whatever I have on the bottom of the first one and the top of the second one, I want them to be the same. So essentially they kind of cancel each other out. Obviously we're going to talk about volume here because I already know dV dt. So if I multiply dV dt by dx dV, the dV on the bottom and the top would cancel and I'm left with dx over dt. Now you might be struggling to figure out how are we going to work out what dx dV is. But remember, this is a cube. You have a formula in your head for the volume of a cube. I obviously need a formula that relates the volume of a cube to x, where x refers to the length or the width or the height. If I asked you to get the volume of a cube, the volume of a cube is simply length by width by height, or the 3 dimensions multiplied by each other. In this case, it would be x multiplied by x multiplied by x. Or in other words, the volume of this cube is simply x cubed. Now I have an equation with v relative to x. And I want to guess, obviously I'm looking for the derivative here. So I'm going to differentiate, and if I differentiate here, I'll get dv dx. The derivative of x cubed is simply 3x squared. Notice that I'm not looking for dv dx, I'm looking for dx over dv. At the moment I know that dv over dx is 3x squared over 1. If I want dx over dv, I just flip them, I want its reciprocal. So I'll write this as dx over dv is equal to 1 over 3x squared. And now I'm happy out. dv dt is minus 1 over 20, dx dv is 1 over 3x squared. If I multiply dv dt by dx dv, I'm left with what I'm looking for, dx dt, the rate of change of x. So if we simply sub in here, it's sorry, I'm going the wrong way around. It's 1 over 3x squared times minus 1 over 20. And if you multiply this out, it's a plus by a minus, which is a minus. 1 by 1 is simply 1. 3x squared by 20 is 60x squared. So the rate of change of x, dx dt, is minus 1 over 60x squared. However, they've asked me to find the rate of change of x at a specific time, at a specific moment. That moment being when the volume is equal to 1 over 64. Obviously, the volume is no good to me in terms of what I have here. I need to work out what is x when the volume is 1 over 64. Well, I've already worked out the volume is equal to x cubed. And at this specific moment we're talking about here, that is equal to 1 over 64. In other words, I want to find the value of x when x cubed is equal to 1 over 64, when the volume of this cube is equal to 1 over 64. It's easy enough, we can almost do it in our heads here. If x cubed is equal to 1 over 64, to get x on its own, you just get the cubic root of both sides. The cubic root of the left-hand side will just give me x. The cubic root of 1 over 64, that's just simply 1 over 4, or 1/4. So at the specific moment they're talking about in this question, when the volume is 1 over 64, the dimension, each dimension, its length is 1/4. 1/4 of a centimetre. So that means that's what I'm going to sub in here. To get my final answer, it's minus 1 over 60, and I'm going to write this as 0.25 rather than 1/4, just to avoid having an extra fraction. So, and it's x squared, so it's 0.25 to be squared. If you plug all of that into your calculator, we get to our final answer. The rate of change of x when the volume is 1 over 64 is equal to minus 4 over 15. And students often forget about their units. My units, think back to what we did at the very start. dv dt was centimeters cubed per second. dx dt, well, dx is a length or a width or a height that's measured in centimeters, and time in this case is measured in seconds. So my answer is minus 4 over 15 centimeters per second.